Hello, my name is Joseph Key, and today I'll be sharing with you just a little bit about the Wankel rotary engine. So without any further delay, let's get started. So let's start off with just a little bit of history. The Wankel engine was conceived and developed by German engineer Felix Wankel, and he patented it in 1929, but his first working prototype didn't get built until 1957, and this was dubbed the DKM-54. However, this first iteration was very overcomplicated, where both the rotor and the housing actually rotated about separate axes. As you might imagine, this was impractical. And stripped down was required just to change the spark plugs. It was definitely not a user-friendly engine. Later in 1957, a colleague of Wankel developed the KKM-57, which is a simplified version, ended up fixing the housing and keeping the spinning rotor, and this simplified version is the basis for all modern Wankel engines. So, why is the Wankel engine even considered? What's wrong with the reciprocating piston engine? Well, there are a number of reasons, but the main thing that the Wankel has going for it is the fact that it uses rotational inertia in its favor. Since it's a unidirectional rotating body, it doesn't change directions. In a reciprocating piston engine, the piston is changing directions 4 times, at least for a 4-stroke engine. And this constantly changing direction introduces cyclic fatigue loadings, which will reduce the life of the parts and require them to be a lot stronger. Now, the Wankel does not need to do this because it has no cyclic loadings. And because it is unidirectional, it can go up to higher RPMs, which would also enable for higher power outputs, and it also results in less vibrations. But the Wankel's design is simple. It only has a few rotating parts, just the rotor moving inside the housing. Whereas in a reciprocating piston, you have the piston head, you have the connecting rods, you have the crankshaft, you have valves, all of that. The Wankel engine doesn't even have valves, so it doesn't need any of that, and it's very attractive from that standpoint. Also, potential for 2 times the power density of a 4-stroke engine, just due to the fact that there are 1 power stroke per revolution, which is twice that for a 4-stroke engine. Now, however, as you all probably know, Wankel engines are not the standard engine used today. That's because they do have some disadvantages. Probably the main one being that they are almost 100 years behind the development of the reciprocating piston engine. This means that engine will always have higher developments than the Wankel, no matter how much it's being worked on. And then there's the notorious sealing issues with the apex seals, which had to undergo extremely high pressures and fail very frequently. Also did not provide very good sealing qualities. And due to the fact that the seals, how they're located inside the housing, by design, the engine is forced to burn oil, which of course reduces efficiency and increases emissions, which is probably the biggest nail in the coffin, especially in today's highly regulated automobile world. Another disadvantage is the fact that these engines produce lower torque. The geometry of the Wankel engine is very complex and based on mathematical functions. So, the housing is shaped like an epipetroid, which is a curve formed by tracing a single point on a circle as it rolls on the outside of another circle, as you can see in the animation to the right. And the rotor is shaped approximately like a rouleau triangle, but it's flattened somewhat on its faces. Now, these rather strange geometries interact in a way such that the apexes of the rotor can contact the inner surface of the shape at all times. These are what you might call a family of curves that are designed to fit each other. So how does the Wankel actually operate? Well, as you can see from the animation, it orbits the inside of the housing, and the rotor's apexes are in constant contact with the inner surface. And there are 3 power strokes per rotor revolution. So as you can see, it's intake, compression, ignition, and exhaust. And per every revolution, since it's a 3-sided rotor, that means there's 3 power strokes per revolution. And the power is transmitted to a shaft. As you can see, there's 2 gears, 2 synchronized gears. 1 rotor revolution will equal 3 shaft revolutions, which means the shaft is going 3 times as fast as the rotor. This comes out to 1 power stroke per 1 shaft revolution. Now, as previously mentioned, this is twice as much as the 1 power stroke per every 2 revolutions for a 4-stroke engine. This is why you can get effectively twice the power density out of a Wankel. One of the issues of the Wankel is in fact its combustion chambers, as you can see in the animation, are very long and thin. This means that the burn rate is going to be very slow. Now, often, as can be seen in the animation, there are 2 spark plugs to help create a more even burn rate. However, most of the time, the fuel is not completely burned and ends up being expelled out the exhaust, which is a reason for the poor emissions and very poor efficiency as well. Now, instead of just an animation, I'm actually going to show you a real live video of the Wankel engine in operation. I put some labels up to show the intake, compression, ignition, and exhaust following each a single cycle. So hopefully that gave you a little bit of a better idea of how the Wankel actually works, being able to see it in real life in slow motion. As far as thermodynamics goes, the Wankel engine operates basically on a 4-stroke Otto cycle. As you can see from the PV diagram to the right, the Wankel engine has a slightly higher max pressure than its counterpart reciprocating piston engine. And theoretically, we would expect this to produce more work, since there's more area inside the curve, greater thermal efficiency, because the thermal efficiency of an Otto cycle is given by 1 minus 1 over R to the K minus 1, where R is the pressure ratio. So if we have a larger pressure ratio, that would be in the denominator, so that'd be smaller numbers being subtracted from 1, so that results in a higher thermal efficiency. And we would expect greater power from the Wankel, just from our previous discussion of being able to get in twice the power density. So from an actual mathematical model, for given specifications, the piston engine produced 212.876 joules, while the Wankel produced 213.043 joules, which is a very small increase in 0.79%. As far as thermal efficiency goes, in the same mathematical model, the piston engine had 47.2524%, while the Wankel had the marginally larger 47.29%. Again, this is only an increase of 0.038%, so that is very marginal. As far as power goes, the piston engine produced 3,547.9 watts, while the Wankel engine produced 4,734.2 watts, which is a 33.4% increase. Now, we would expect it to be an 100% increase, because it should have twice the power density, but it is very possible that this mathematical model didn't have all variables set equal, perhaps with different burn rates, etc. But there is an increase, which matches with the theoretical. So, theory aside, how does the Wankel engine play out in real life? Well, if we take 2 vehicles, the 2011 Mazda RX-8, which is the last vehicle produced with the Wankel engine, and the 2015 Corvette Stingray, we can see what's really going on. So for the Mazda, the engine is 1.3 liters and is 232 horsepower. And with the Stingray, we've got 6.2 liters and 455 horsepower V8 engine. So for the Mazda, that's a power density of 179 horsepower per liter versus the Corvette, which is 74 horsepower per liter. Now, just going along with theory, that matches very well, because we have 142% greater power density for the Wankel versus the traditional V8. And that is actually 40% more than theory, because theoretically it would be a 100% increase, but in this case, for whatever reason, it was 142%. However, the caveat is that the highway mileage of the Mazda is 23 miles per gallon versus that of the Stingray is 29 miles per gallon. That means that even though the Mazda has only half the power, it still has 21% worse fuel economy. Now, this is due to all of the reasons we mentioned before: the leaking seals, the burning oil, the unburned fuel, just the poor emissions and efficiency, and this is why Wankel engines are not used widely today. However, the very concept of rotary is still not completely out of the picture, as there are other designs, such as the liquid piston, which has received millions of dollars in DARPA funding. So in the future, we hope that rotary engines continue to be developed, as they do have benefits, as previously mentioned, like the use of rotational inertia. So, hope you found some of this helpful, and have a great day.